but it turns out it's H plus when it loses an electron, but when we gain an electron, we're essentially a hydride with a lone pair of electrons and that negative charge. You also learned about hydrogenation of alkenes, as well as stereochemistry. That's going to start to come up more and more often. And also please review, and we'll see if we have enough time at the end of class to review some of these other reactions across alkenes to make alcohols. All right, so we've moved into another chapter, actually, chapter 16. So we'll do just a quick recap of chapter 15 today, and then get started on these learning objectives about how to make alcohols. Alcohols are a really important functional group that we see all the time, and so we already learned how to make alcohols with organometallic reagents, but here's a number of different ways we can do that. All right, so let's just do a pretty quick review of chapter 15, what we learned. We only spent one day on chapter 15, which makes me sad because it's my very favorite topic in chemistry, but if you were intrigued by it, I teach an entire class, a whole semester on organometallic chemistry. So one thing I wanted to review was the fact that any type of organometallic will work in a reaction. So we don't need to worry, is it magnesium, or is lithium, or is it sodium? In this case, for the purposes of this class, we don't distinguish any issues between those. Sometimes we do have reagents that only work for one thing or another. So thinking about a retrosynthesis of our alcohols, perhaps we had something that looked a little bit like this. And we could think about two retrosyntheses of this. I'll just go over one. For example, if we were to break the bond at this position, for example, you could be equally correct to break it at the other position with a different set of organometallic reagents. We would start out with our benzaldehyde, or this phenylaldehyde here. And then we could use our Grignard reagent or our organomagnesium reagent, or it really doesn't matter, we could use a lithium reagent. So there's not something special about magnesium versus lithium. You could use sodium if you wanted as well. Again, there's oftentimes a lot of correct answers here. So if we were to take this molecule, we were to break it at this position, we could have an equally correct answer. A retrosynthetic analysis would be taking our phenyl group as the organometallic. So the magnesium bromide, or actually in this case, let me put chloride just so you can see. The counterion doesn't matter as well. Or we could use phenyllithium as our organometallic. It really does not matter. And then, of course, we would need our aldehyde, which has this isopropyl group on it, right? So these are kind of mix and match. That's good for you in case, you're doing a multi-step synthesis. You can use either one. Obviously, the conditions to make the organometallics are slightly different in the fact that, you use two equivalents of lithium. All right, and then the other thing I wanted to review is the fact that we use non-protic solvents. Right? We talked about the fact that organometallics are often used as bases. So if you have a proton there, so we can use something like ethers or tetrahydrofuran, so that's THF, because protic solvents react. And we don't want to make something in a solvent in which it just reacts, right? So I'm bringing this point up because at the end of the day, what we get out is a deprotonated alkoxide, not the protonated alcohol. So in a separate step, not the same one, in a separate step, we use H3O plus, or whatever acid you want, HCl, sulfuric acid, doesn't matter to me, plus, not plus, but or water. to protonate to form the final alcohol. So those are the three sort of bullet points that are the main takeaways, right? We can sort of have a mix and match scenario with organometallic. We have a mix and match scenario about which bond to break to make the alcohol with an organometallic. Sometimes there is only one option, for example, but in this case, we have multiple options for which bonds to break. We use protic solvents, otherwise our organometallics would quench and they would also catch on fire. And then in a separate step, we need to protonate off to form our alcohol product. All right, so that's chapter 15. And the reason why we're reviewing this is some of the stuff that we're gonna use today are actually, I alluded to the fact we're gonna use hydrides, H-. So we use carbon- in that last chapter with organometallic. So actually hydrides, H-, react remarkably similar. We have to think about proton sources as well. And so it kind of goes pretty well with organometallics. All right, so our first learning objective in chapter 16 is 16A, and it's a 2Ps. So it's a 2Ps of formation of alcohols. You're going to see that is a big topic for this chapter. So always forming alcohols, but our learning objectives are differentiated because it's the different routes that we're going to use. So the formation of alcohols, in this case, it's from aldehydes and ketones. Through hydrogenation. All right, we're going to use H2. You've seen this before in chapter 8, and in this case, it's 16.2. All right, so let's take our learning objective. We can piece it apart. We know our starting material, for example, is going to be an aldehyde or a ketone. So you will recall that this is what the structure of an aldehyde is. We can draw the H in, or sometimes we don't draw it in. It doesn't matter. All right, so the R groups here, as we said, is a carbon-based group. So we can have alkyl groups, aryl groups, vinyl groups. Means there's a double bond. And alkynyl groups. So these are very, very generic reactions. They work with a lot of different things. All right, so our learning objective says this is through hydrogenation, and when we hydrogenate things, we often use hydrogen gas, so H2. So in this case, just like in our electrophilic aromatic substitution reactions, we actually need a catalyst here. So we're going to look at the D block of our transition metals, and we're going to mostly focus on group 10 metals. So that's element number 28, nickel, 46, palladium, 78, platinum. Group 10 metals are also an area of expertise in my group. So we can use a nickel catalyst, or a palladium catalyst, or a platinum catalyst, or another element, ruthenium. So ruthenium is pretty close on the periodic table, but we slide over to element number 44. It's a secondary transition metal. So any of these catalysts will work. So if you just want to choose your favorite one to always use, that's fine with me. And the product that we're going to get out is going to be our alcohol. And we still have our aldehyde proton. Nothing's happened to that, but we've essentially added H2 across our double bond. So what that looks like is a product that looks like this. All right, so our H2 has one bond to the alcohol and one bond to the carbon. And when we use an aldehyde, we're going to end up with a primary alcohol. Right, so when we say primary, secondary, sometimes we're referring to how many atoms are on that particular atom of interest. But in this case, for a primary alcohol, we're really focusing here that there's a single R group here. So this is the primary group, all right? There's 2 hydrogens, and it's a primary alcohol. All right, so our learning objective also says that we can use ketones. Be substituted symmetrically or unsymmetrically, the same R groups apply. And you guessed it, we can use the same reagents. So we can use our H2 as well as our nickel, palladium, platinum, or ruthenium catalyst. And then we're going to make a secondary alcohol. And it's secondary because we have these 2 R groups. We've added across that double bond, all right? So here's our secondary alcohol that we can form here. All right, so something that we need to be a little bit careful with, this is why we needed those 2301 review topics. I'm just gonna move that up a little so I can add a bullet point. All right, so when using H2, we need to worry about other functional groups. You learned H2 can be used to hydrogenate an alkene. So when using H2, in order to make an alcohol, we need to be careful about alkenes and alkynes. Right, because those multiple bonds can get hydrogenated. So the next learning objective will help us get around that issue, but hydrogen on these catalysts is very easy to use. So this is something, a term I've used before, but never really defined. This is called functional group compatibility. All right. So when you're thinking about the molecules we make in this class, we're sort of learning, believe it or not, the basics of organic chemistry. It might seem really complicated, but when you take a look at this molecule that Brandon and the Lamb group had made, we see many different functional groups here. We see benzene rings, we see cyano groups, we see carbozols, we see halides. So organic molecules are really, really complicated, and we have to look and we have to see if every single functional group on a molecule is going to be compatible with the conditions that we want to use in a reaction. And this is one of the reasons why so many reactions exist in organic chemistry, because if you really want to make a secondary alcohol, but you have an alkene, you can't do it with this method. So we had to develop another method. All right, so that brings us to our next learning objective. This is learning objective 16B, and this is going to be a 4P, and again, it's the 4 Ps of formation of alcohols. And again, this is going to be from aldehydes and ketones, just like we had before. But unlike previously where it was through hydrogenation, this is going to be through reduction with hydride sources. All right, so as I alluded to in the review topics, hydride is H minus, has a lone pair of electrons on it. All right, let me introduce you to some of our hydride reagents, all right? So we're going to use a hydride reagent called sodium borohydride. And essentially what this is sodium is plus and borohydride is minus. All right, so why is boron minus? Well, when we take a look at the periodic table, it's our element that's next to carbon, element number 5 on the periodic table. And boron only needs 3 bonds to it. And as soon as you add 4 bonds to it, well, now it has a full octet. It is negatively charged, right? Just like we had 4 bonds of carbon, we go 1 element over, we only need 3 bonds. All right, sodium borohydride is the source of H minus. All right, it's a hydride source, not proton. This is a point of confusion every single year on exams. All right, so there's a couple of quirks about sodium borohydride. It's actually not a very strong reagent. It's not a very strong nucleophilic source of hydride, or it's not very hydridic, you could say. So in this case, we need an alcoholic solvent. All right, because we need a proton source, H plus source. So essentially what we had before with hydrogen is we had an H plus and an H minus built into our reagent of H2. Now here we need to build in, because at the end of the day, we're forming alcohol just like we saw before. And this could have come from H minus adding to the electrophilic carbonyl. And then this came from H plus, all right? So in this case, we need an H minus and we need an H plus source. All right, so there's another stronger reducing reagent that I'm going to introduce you to, and this is lithium aluminum hydride. So lithium is positively charged in this case, aluminum is negatively charged. Take a look at the periodic table. Aluminum is directly under boron, so element number 13. All right, so this is lithium aluminum hydride. Sometimes we call this LAH, or lithium aluminum hydride. It's kind of a mouthful to say a lithium aluminum hydride. So we do abbreviate it sometimes. All right, so this is a stronger source of H minus, more hydridic. So, you know, this might be a weird concept, but actually when we think about it, acids have different strengths, right? We know that HCl is an acid, is a very strong acid, and trifluoroacetic acid is pretty strong, but acetic acid is pretty weak, right? So at the end of the day, it makes sense that hydrides have different strength or weakness. In this case, water or H plus source is added in a separate step, just like we saw with organometallics. And the reason is this is a stronger source of hydride, so it's H minus. When H minus finds H plus, they just sort of quench each other, all right? So that's the difference between these two different reagents. And we're going to learn and sort of compare and contrast some of their characteristics. All right, so at the end of the day, what we have is our aldehyde or our ketone. And we can use 2 sets of conditions. We can either use lithium aluminum hydride in one step, and in the second step we can add in water, or we could use a second set of conditions, which is sodium borohydride and an alcoholic solvent. So we'll just say ROH, R meaning methanol, ethanol, isopropanol, terbutanol, whatever you want. And at the end of the day, our product is going to be our alcohol. So I'm going to draw these in a separate color. Right, so we've added an H plus and an H minus into our reaction. All right, so we're going to compare and contrast these, but first we're going to get to P4. This is kind of a wild mechanism. So I don't know, it's fun for some people. All right, so this is our reagents. As we said before, we think of this as a hydride, so that's a nucleophile in the reaction. So here we can say this is our electrophile, and in this case, H minus, our hydride, is our nucleophile. All right. So let's start with a ketone. So this is P4. All right, so what does borohydride or aluminum hydride look like? Well, it's a tetrahedral molecule, as you might imagine. So we have our boron that is bound to 4 hydrides. And is negatively charged. We'll just carry through our sodium counterion, as always. So wedge. All right, so these are hydrides, H minus equivalents, all right? So that means when we're thinking about where electron density lies, just like with organometallics, we're going to take the beginning of our arrow is going to start between the boron hydride bond, because that's where the electron density is, all right? So our first arrow is just attack of our nucleophilic hydride up into our electrophilic carbon position. Then that causes us, just like with organometallics, you'll notice the mechanism is very similar. That causes us to break our carbon-oxygen double bond and place our electrons onto our oxygen. All right, so that's step number 2. And then in a third step, because our boron has now lost a bond to it, it's a good Lewis acid, and actually we get one of the lone pairs on oxygen that comes and attacks boron. But it has to happen in this sequence of steps. That nucleophilic addition needs to happen first, so we break that boron hydrogen bond. So that's why the series of arrows goes in 1, 2, 3. All right, so the first steps are just like organometallic reagent reactivity. And that third step is a little bit new to us, but actually it's just like a nucleophile coordinating to a Lewis acid, because that's exactly what it is. All right, so when we put that lone pair of electrons on oxygen, that means we have 2 lone pairs left. We can draw in our hydride that is now added to our base of our carbonyl, and now we have our boron, which now has 3 hydrides on it, and our oxygen. So that's still negatively charged. And then we carry our counterion through. All right, so at the end of the day, this is going to happen 3 times. All right, so this boron is going to go ahead and attack another equivalent of a carbonyl, et cetera, right? This is going to happen over and over and over again. And then after 3 times of happening, the product that we're going to get out is going to, I'll draw it down here, is going to be boron that is now bound to 3 equivalents of our alcohol. Right, because this has happened 3 times. All right, because boron is going to have 4 bonds to it, it's still negatively charged. We can draw in where all of our hydrides have gone to the base of all of our carbonyl carbons 4 times. And we still have our sodium counterion. All right, I'll give you a moment to draw that. All it is, you know, what our first series of 3 arrows happening a total of 4 times. And then, that's not our product. There's a reason why we need that alcohol solvent, because that's going to get us to our product. All right, so we'll bring in our alcohol solvent. So let's just use methanol in this case. All right, so this is methanol as our alcohol solvent. What's going to happen at that point is our exact same sequence as we sort of had seen before with our Lewis acid being involved. So essentially the lone pair of electrons on our oxygen is going to deprotonate that methanol. That's going to break that OH bond, and it's going to return those electrons to our alcohol. And then that alcohol is going to go ahead in the third arrow and attack back our boron. All right, so arrow number 1 is protonation of the alcohol that we've reduced. Arrow number 2 is that sort of deprotonation sequence, and arrow number 3 is forming our boron reagent. So this happens a total of 4 times total. What we get out at the end is 4 equivalents of our alcohol, which you can see has a hydride bound to it from our sodium borohydride and our hydrogen H+, essentially acid, bound to that oxygen. The byproduct of this reaction, to help us understand that this happens 4 times, is going to just be our methanol that's bound to our boron. Still negatively charged boron, and we have our sodium plus cation. All right. So it looks like kind of a crazy, complicated mechanism, but at the end of the day, you know, it's really just very similar to our organometallic mechanisms. We needed that proton. All right, so lithium aluminum hydride is the same mechanism. All right, so how it's the same is that instead of a boron here, you would just put aluminum. Same mechanism, right? And instead of methanol being in that same step, we would just use water as our proton source, all right? In a different step. So the exact same arrows for lithium aluminum hydride. All right, I still see people writing, so I'll give you a moment to catch up. All right. So now let's see, you know, what cases, unlike organometallics, where we can sort of mix and match what we want. As I alluded to, and as I said, lithium aluminum hydride is a much stronger source of H-. So it's actually more powerful and could do more types of reactions. All right. That's our next learning objective, 16C, is the 2 P's of formation of alcohols. Right, so no mechanism involved here. Again, the theme of the chapter is making alcohols. But instead of from ketones and aldehydes, this is going to be from carboxylic acids. Oops, all right, and this is from specific hydride reagents. This is in 16.3. All right. So we cannot use sodium borohydride for this reaction. We have to use lithium aluminum hydride. Okay, so let's get an example here. Say I had this particular carboxylic acid. So carboxylic acids are a higher oxidation state of carbon. They have more bonds to oxygen, so more oxidized. And in this case, we can only use lithium aluminum hydride. And then in a separate step, an H2O or water workup. And what we do in this reaction is we are forming alcohols, just like our learning objective said. The reason why we can't use sodium borohydride is you'll see here we had to deliver 2 equivalents of hydride in this case. So we need a stronger reducing agent because we're taking this oxidation state down from a carboxylic acid all the way down to an alcohol, all right? So that's why we needed a much stronger reducing agent. So lithium aluminum hydride is much stronger of a reducing agent than sodium borohydride. So it is the only hydride reagent that will reduce a carboxylic acid. All right, we're going to have an entire chapter on carboxylic acids and their derivatives. Right. So it's pretty special. So just remember lithium aluminum hydride. I've also suggestively used a special carboxylic acid. You'll notice there's an alkene in this carboxylic acid. Whereas before, when we were talking about functional group compatibility with H2, we couldn't have had that. So that's another reason why lithium aluminum hydride and sodium borohydride also are actually kind of special. All right, and so let's go ahead and have a learning objective on that. So learning objective 16D is compare and contrast H minus or hydride versus H2. All right, so let's use that same alkene example. In this case, we're just gonna reduce an aldehyde or a ketone, not a carboxylic acid. So let's have a similar molecule as we had before, but this time as an aldehyde. All right, so if we were to use our hydride conditions, which was the sodium borohydride and the alcohol solvent, or we could have used lithium aluminum hydride and then water in a separate step. The product of this reaction would only be the reduction of our aldehyde. We would get no reduction of that double bond. So in comparison, we can also reduce down that aldehyde or ketone with our H2 and a catalyst, some sort of metal catalyst. But so we reduce down that carbonyl, but in contrast, we would also end up reducing down our double bond as well. So our product in this case would be the reduction of our ketone, as we saw before, and then also we would reduce down our double bond. Right, so this is always a favorite exam question, functional group compatibility. Right, so H2 will hydrogenate double bonds, but sodium borohydride and a lithium aluminum hydride will not. All right, question. Yeah, that's a great question. So for those of you who couldn't hear, if you were to only add in a single equivalent of H2, would you be able to, it's the word is chemoselectively, reduce down one or the other? This is a pretty unselective reagent and reaction, so you'd end up kind of getting a mixture of both. I think that's a great question because we do sometimes see that if you play around with the stoichiometry, you can only get one product. So I think that's a great question. In this case, hydrogen and the metal catalyst are just a super powerful catalyst, so they'll kind of go unselectively. But that's not always true for all reactions, but it is for this. Great question. All right. So why is this? Another thing that we should think about is what we kind of already talked about before, how these are all reagents are all slightly different from each other. So this is sort of the compare and contrast between lithium aluminum hydride and sodium borohydride versus H2. So let's also have a learning objective about sort of one of the reasons why this is. So that's 16E. So this is to rationalize reactivity of metal hydride bonds and using my very favorite type of rationalization, which is using electronegativity trends. All right, so we're looking at the periodic table here. So when we take a look at boron versus aluminum, we see they are in the same column of the periodic table. So they often is an indication of similar reactivity. But as we go up and down in the column of the periodic table, we see a lot of differences. In this class, we've already noticed some differences in the halogens, for example, that fluorine's kind of special. It reacts different than chlorine, for example. We'll learn about sulfur versus oxygen and how those are quite different. So boron and aluminum are quite different because the electronegativity is different, all right? So we're gonna add another learning objective here, which is 16F, and the example I'm gonna use is gonna help rationalize. So in this case, we're gonna compare and contrast lithium aluminum hydride and sodium borohydride. All right, so we said that if we were to take, for example, an aldehyde here, a carboxylic acid here, we were to react it with sodium borohydride, there would be no reaction. Right, we said it's not strong enough of a hydride reagent. Alternatively, we could turn to our lithium aluminum hydride and our water in a separate step. And we would, in fact, reduce this down. We would react with that carboxylic acid. We'll end up with a fully reduced product to the alcohol. All right. So we already stated that lithium aluminum hydride is a much stronger reducing agent. All right. And this is because aluminum is far less electronegative. It's less electronegative than boron, right? So the aluminum hydride bond is more ionic and more aluminum sort of plus, and H minus. Right, this is the exact same idea that we have with acidity, all right? It's just that the electrons are going to a different atom, right? So when we're thinking of really acidic acids, we think about things that can stabilize charges really well, negative charges really well. So we can have H plus floating over here, and for example, I minus over here. We're thinking about that all the time with acids. Exact same thing going on in hydridic reagents, right? We're thinking about H minus, trying to be dissociative and more hydridic and more nucleophilic, all right? So that is why it's just a periodic trend, all right? Versus boron is much more of a covalent bond. And so those electrons are more shared, less available to reduce a function. All right, so let's check our knowledge with a couple of chime-in questions. So these will be back-to-back, so don't close your chime-in. So we're already on lecture 9 for chime-in. Let's see what you all are thinking for this reaction. All right, so let's go ahead and see if we can recall what the lithium aluminum hydride can be used to reduce. That sodium borohydride cannot. Right, we sort of have H2 in this mix. We have multiple H minus reagents, so we want to make sure that we can differentiate these. All right, looks like everyone's sort of mostly on the same page. So I see where people were thinking with aldehyde and ketone. It can reduce those, but so can sodium borohydride. So sort of our special one that we're thinking about is a carboxylic acid. I also put in the arrow ring here for a reason. The reason is oftentimes people think of arrow rings. Well, that's 3 double bonds, so maybe I need to consider that. With H2 or something like that, it turns out that aromaticity is different than just having double bonds. It's far more stable. It's very hard to hydrogenate a benzene ring. All right, so it looks like everyone sort of answered that question. Great. So now let's go ahead and see the next question that we have. Back. Nope, I guess I deleted the other one. Okay, that's our only chime-in question for today. All right, so these are kind of our considerations with how we think about reducing things. So because we have just a few minutes, I'd like to think about some things that will come up on your homework. So we do have a few minutes to do 2301 quick review here. All right, so this is the 2 P's of hydration of alkenes. Let's see here. All right. So we've seen before alkenes can get hydrogenated, but this is going to come up in your homework, so I'd just like to review it, that they can also undergo addition across them. Right? And so these are acidic conditions. And in this case, what we've done is we have added OH and H across that double bond. So what we've done is we've made an alcohol. Right, and this is the selectivity here is Markovnikov. Right, this will come up in your homework, but this is a review of another way that you've already learned to make alcohols. Right, so this is hydration. You can also think about hydroboration. Oxidation as a sequence. You've already learned about this. So we could take that same alkene. We could have 2 sets of conditions, which is borane or BH3, and then hydrogen peroxide, water. And what we would get here is we would get the other isomer of our alcohol. So this is called anti-Markovnikov selectivity. All right, so you have learned to make alcohols before. This often comes up in the homework, so I just wanted everyone to be aware. All right. All right, so I think we should do a practice problem with some of these reactions about how we can potentially make alcohols. All right. Some of our sort of different methods. All right, so putting it all together, we always have a multi-step synthesis on the exams. So in a multi-step synthesis, you're given, it's the very last question, it's generally the most challenging one. You're given some sort of starting material, right? And then you're given some sort of product. And then it's up to you to learn to build this, right? So in this case, we're going to go through a couple of steps to get to this product here, all right? So seems like we have an alcohol that we're forming. So in the last chapter, we sort of would have broken our alcohol at that position there, all right? And that means in order to make that molecule, we would have needed an aldehyde, all right, for that right side half. And we would need an organometallic to be able to make that. All right, so we might add some other organometallic like NBULI as a base. And then we could go ahead and make the lithium salt of that, and that would be our sequence to make that molecule. All right, so I thought backwards from the end point, that final product that we would want. But if you wanted to have a different starting material, for example, which we will learn how to make on Friday, you could have started with this reaction and used some of our new chemistry that we learned today, such as sodium borohydride, to do this reaction using an alcoholic solvent. And we could have done that reduction a very different way. In the top sequence, we made a carbon-carbon bond. In this case, we've just done a reduction. All right. Now, say we had another product that we wanted to make. Right? This is going to be the same number of carbons. All right. And we can get there from two ways. We can get there from both of our products. Right? So in our top sequence, we could have taken this and we could add in H2 and a palladium catalyst. Or we could have started from our other starting material and used those same conditions. All right, so these are the types of things that I'd like everyone to think about practicing. Is now that we know how to make alcohols in many different ways, we need to start putting it together and saying, well, this method can make an alcohol, this other method can make an alcohol, and this third method can make an alcohol. And that's going to serve you really well on that final problem on the exam.